I'm just going to start giving my talk. Okay, so it will be, as already announced, on nonlinear acoustics waves, and it's supposed to be really an overview talk. So there will be basically no mathematical details. I hope you are not disappointed about this, but it's just my, so to say, my secret or less secret goal is to kind of introduce you to this exciting field and maybe attract your interest to it. So I will start with a bit of modeling. Most of the talk will be taken up by analysis, but again, a disclaimer on details. And if time permits, I would like also to say something about some numerical and also optimization aspects. So, oh, this is maybe not the right way of putting the screen, sorry. Should put it to presentation, yes. So this was joint work with many people. You will see some of them in the references I give. And it was also supported, of course, by some funding, mainly by the Austrian Science Fund. So what's it all about nonlinear acoustic wave propagation? Maybe that's best explained by means of some pictures. And here are some temporal snapshots of a scenario that you will also see later on in the talk. Namely, this is from some application of nonlinear acoustics in high intensity focused ultrasound, where the ultrasound travels, is excited here. So this is just a half view of a full setup, and it's also a cross section also of a setup. So it's, it's, if you think of it rotationally invariant, then it's just the essential information that you see here. And so the acoustic wave is excited over here. Then it travels through this lens, which is the darker blue, and then it continues traveling through this light blue fluid. And you see in the second snapshot, as it travels through the fluid, eventually it gets focused. That's because of that lens. But the focusing is not exactly as one would expect in a linear wave propagation. And this can be better seen by this second set of snapshots from a different experiment. Here the wave is, a sinusoidal wave is excited here on the left-hand boundary, and it keeps being excited. But as it travels through the medium, you see that it's of course damped, but it's also steepening up. So at the end, you see this sawteeth, as it's also called, behavior that is due to the fact that basically at this amplitude, the wave has a higher speed than at this negative amplitude. And so you will see also in the equations that the effective speed of sound depends on the pressure, basically, or on the amplitude of the wave. The motivation for studying nonlinear acoustic wave propagation comes from the many applications of high intensity focused ultrasound. So for example, in lithotripsy, which is actually the background of the first picture I've shown you, but also thermotherapy. So there's several medical applications, but also industrial applications like cleaning or welding. But well, that's the one that we are most interested in actually, also in our optimization problems. And for this purpose, one can use different setups. The one that I've shown you basically is this one over here. So the ultrasound waves are excited by some electromechanical principle down here, go through this membrane, and then they are, so to say, pushed into the fluid medium. They travel through the lens, and then they are eventually focused. Ideally, they would be focused at a point, for instance, well, not for instance, ideally at the point where the thing that is to be destroyed sits, and so kidney stones, for example. But due to the nonlinear propagation, this focus is usually elongated and not sufficiently well localized. And that's why also engineers started studying this problem. So the finite element simulations and so on and so forth. And well, the mathematical analysis only came a bit later. Another principle of focusing comes by this kind of bowl-shaped piezoelectric array. So this is an array of piezoelectric transducers that can be excited separately in principle. And by this, and also by the shape of this array here, focusing takes place. So also the light blue region is the one where nonlinear wave propagation takes place. So the plan of this talk is to say something a bit, at least, about modeling and about the fundamental models of nonlinear acoustics. Then a bit more about analysis, and I particularly will dwell on singular limits of several kinds, but also a bit on coupling that arises naturally. Let me go back, for instance, between this lens and the surrounding fluid. Then, if time permits, I will say a bit about some numerical aspects, namely, well, of course, efficient numerical solvers are an important point, but I will focus on a certain aspect that is related to wave propagation, so free space wave propagation, avoiding artificial reflections. That's done by non-reflecting boundary conditions. And then finally, something about the optimization problems that are related to these focusing tasks. So the basics of modeling come from the basics of acoustics. And so the main quantities in acoustics are the acoustic particle velocity, acoustic pressure, and mass density. All of them depend on space and time. And usually they are decomposed into a mean part that is constant in space and time, and a fluctuating part. So the mean part is always the one denoted by 0, and the fluctuating part denoted by this tilde here. So we are going to look at the situation where actually only the pressure and the mass density has a non-zero mean value, whereas the velocity has a vanishing mean value, meaning that we don't consider flow problems, but really just acoustic wave propagation. Now, the governing equations for these quantities are, first of all, conservation of momentum, using the fact that in our settings, usually the velocity is irrotational. It looks like this. Then conservation of mass, which is also sometimes called equation of continuity in that context. And the state equation, which is an equation that relates, so to say, a material law between the mass density and the pressure, or actually the fluctuating part of the mass density and the pressure. So the c square down here, or actually the c itself, is the speed of sound. All other constants, I did not put the names on the slides because they are not so important for the mathematical analysis. So how do we get to wave equations? Actually, what I would like to show you is how to derive second order wave equations, as you are used to probably from your PDE course. And so just to give you an idea on how these more general models, or nonlinear models actually, that you will see a few slides later, are derived, I would like to do the derivation just of the linear wave equation, as you probably know it already from these balance laws and this, so to say, material law down here. So the linear part is just the one that is highlighted in red. Well, you would maybe say that also this part is linear, but it's related to some dissipative or viscous effect. And so therefore, at first order, it is supposed to be skipped in the derivation of acoustic equations. So it's the linearized balance of momentum, the linearized balance of mass, and this linearized relation between mass density and pressure via the speed of sound. And let me recall that for the mean values, so for instance, for this rho 0 appearing here, any time or space the derivative just vanishes. And so this gradient of P is just the gradient of the fluctuating quantity. And likewise, for instance, this rho T is just the time derivative of its fluctuating part. Okay, now I just copy over the linear parts of these balance equations. balance of momentum and balance of mass. And back here, I just plug in the equation of state. And now, in order to eliminate this velocity here, it's quite straightforward. You see immediately, just take the divergence of the first equation, take the time derivative of the second equation and subtract. And then V is eliminated and you end up with the well-known wave equation as it's encountered in any basic PDE course. It contains the speed of sound, the constant speed of sound. You will see later on that in the nonlinear wave equations, one will encounter what one might call an effective speed of sound, something which also itself depends on the pressure. So going back to the fully nonlinear balance equations, in principle, in the same way, so taking the divergence of this first equation and subtracting the time derivative of the second equation, one ends up with a second order wave equation. But of course, there are some terms left, and physicists know how to skip terms. I learned about this a bit, but I would not dare to skip terms on my own, so I follow the rules. And doing so, one ends up with Kuznetsov's equation. That's the classical model of nonlinear acoustics. You can still recognize it as a second order wave equation for the pressure over here. It has a strong damping term. You will see later on there might be different damping terms eventually. And it has a quadratic nonlinearity, actually two of them, one related to the pressure and one related to the velocity. So the velocity is not completely eliminated from this equation by this elimination scheme. And so we have to also take into account this relation between velocity and pressure, which is actually the linearized balance of momentum equation. And also notice that these quadratic nonlinearities are under a second time derivative. So it's relatively high order nonlinearities that we have to deal with here. One can write this also as an equation for just a scalar variable. So at the moment now, it's still an equation for a scalar and a vectorial variable, namely the pressure and the velocity. But take into account the fact that the velocity is irrotational. One can write it as the gradient of a scalar potential. Physicists and engineers always write a minus here, so I join them doing so. And we end up with this equation. It's just a scalar equation for a single state. And well, it's still also in terms of psi, it's still basically a second order wave equation. Starting from Kuznetsov's equation, one can do further simplifications. The first of these is to get rid of this velocity term by what is usually called neglecting local nonlinear effects. That is doing this approximation here. So approximating the quadratic velocity term by another quadratic pressure term, and then one ends up with the Westervelt equation, which is also used very often in simulations of nonlinear acoustic waves. So it's written in terms of the pressure as opposed to the velocity potential for Kuznetsov's equation. But again, what we see here is a quadratic nonlinearity under a second time derivative. So further simplifications are these. First of all, if we assume that there is a preferred direction of sound propagation, in this case it's the x direction, then one ends up with the KZK equation. So this one here, which is also sometimes called parabolic approximation of the Kuznetsov equation, or the Westervelt equation. So it comes here with the Westervelt type quadratic nonlinearity and in pressure formulation. And then another equation that is also known, very well known from textbooks, and is very often used as an example for all kinds of phenomena, is Berger's equation, so which arises if we go to one single dimension in space. So the tau here is the retarded time. Actually, it's Viscous-Berger's equation because we have this damping term here. Okay, one can also go the other direction and look at more complicated models. So take into account more physical phenomena. So for instance, taking into account also energy balances and temperature equations for the temperature and the heat flux. One ends up with the Blackstock-Crichton equation, which looks like this. I've written it here in such a way that you can maybe recognize it partly as Kuznetsov's equation, which is also copied down here. So that's the linear part of Kuznetsov's equation. Also, the nonlinear part of Kuznetsov's equation appears over here. Note that there's another time derivative, because also here we have another time derivative. Not only time derivative, it's actually the whole heat operator that acts on this linearized Kuznetsov part. And there's something which in this setting one can, although it's not really low order, but as compared to the terms over here, it's relatively low order. So it's some type of remainder term. Another approach comes from the desire to remove the infinite speed of sound phenomenon that arises in Kuznetsov's equation. That's basically due to the strong damping term here. And it's done actually, physicists do this not by just skipping this damping term, because damping is clearly there, so one cannot just skip it, but by introducing another third order term, which comes with a relaxation time, which is denoted by tau here. We will see both equations, Blackstock-Crichton and the JMGT equation, later on, and looking at limits as this A tends to 0 or this tau tends to 0, which should, of course, give Kuznetsov's equation. It does so formally, but it will also do so mathematically. So this is a slide that just supposed to give an impression that there's a lot of literature around, and all these dots are disclaimers for certainly not having taken into account. Actually, I should have put dots down here as well, sorry, for, well, just simply not being able to put all the references that arise recently in this field. So just to give you a flavor on what the analysis of these equations means, if you took a glimpse in the previous slide, so there's also work on the Cauchy problem, so on all of Rn, so this should be an R, actually a D, sorry. What we are going to look at here is usually bounded domains with boundary conditions. Later on, we will see special boundary conditions, namely non-reflecting one. So this type of boundary conditions in homogeneous Neumann can, for instance, be used to model excitation of ultrasound waves. We also, of course, we need initial conditions on U and UT, where U is, for example, the pressure, and here is for example, the Westerveld equation with a simplified writing for the constants. But, well, a similar setting can also be considered for these other and higher order models. And what is particularly challenging in this context is this second time derivative over here, because if you do the derivative using product rule, chain rule, actually, and product rule afterwards, you end up with this term back here, where this quadratic term here is relatively harmless, but this one is less so, because it comes with the second time derivative of u. So actually this should go over to the other side. Let's do that. And then it becomes a nonlinear coefficient in front of the second time derivative. So that's why this is a quasi-linear wave equation. And of course, if the amplitude is too large, then this coefficient could become negative or 0, and then this equation would simply degenerate, meaning that the model is not really valid anymore. So also in the analysis, of course, in order to keep this a wave-like analysis, one has to avoid this term here becoming 0 or negative. And this happens not only in this Westervelt equation, but also in the others. So our first approach to this was to employ energy estimates using the fact that we have this nice strong damping term here. By using appropriate multipliers, one can get a bound on the H2 norm of U with respect to space and continuous with respect to time. And using the embedding of this H2 of omega into L infinity, one gets a bound on U, one gets an L infinity bound on U. So this was our initial approach. There are much refined approaches, meanwhile, doing this in LP spaces and also using interpolation, so in order not to have to use this full H2 and so on and so forth. But that's the, so to say, basic strategy in order to avoid degeneracy here. And well, since it's U itself that appears in here, one has to sort of bootstrap this non-degeneracy by some kind of fixed point argument. Now let me move on to the singular limits. So taking some of these parameters that you have seen in the equations to 0 or to something else actually. And let me start with the Blackstock-Crichton equation. So you have seen that at least formally it's related to Kuznetsov's equation. So in the limit, or just formally setting a to 0 here and taking a time integral, so removing one of these time derivatives, one ends up with Kuznetsov's equation. So let me point out that when sending a to 0, also this r here goes away. So to what extent can this be made mathematically rigorous? Well, the question is, if you look at this as a family of equations and the corresponding solutions as a family of solutions, the question is, will this family of solutions converge as a tends to 0? In which norm does it converge? And will the limiting solution, so the limit of this sequence or of this family of solutions as a tends to 0, really solve Kuznetsov's equation? And well, this is just to point out it can be done, and it has been done in appropriate spaces. So the strategy in principle is to derive energy estimates on solutions by using appropriate multipliers, and then picking out the terms that are independent of A, because these are those that survive taking limits. And then that's the resulting norm is hopefully still sufficiently strong in order to establish the limiting solution as a solution to Kuznetsov's equation. So one thing that I would like to point out in this context is that since we move from a third order in time equation to a second order in time equation by this limiting process, in order to preserve regularity, we need compatibility of the initial data. That's clear. So since this is a third order in time equation, of course, we need not only 2, but 3 initial conditions. And the one on the second derivative, so the psi 2 here, has to be compatible in the sense that, so to say, the PDE at time 0 needs to be satisfied. Otherwise, one might still be able to show existence of solutions to exhibiting boundary layers and so on and so forth, but they will possibly not be regular enough to be able to deal with these nonlinearities. Okay, the second advanced model that I've shown you is this JMGT equation here, where we have the relaxation time tau in front of the third time derivative. Not only there, also here. And again, just setting tau equal to 0, one ends up with Kuznetsov's equation. And also here the question arises, does this hold also in a rigorous sense? In which function spaces does it hold? Again, the strategy is to get uniform energy estimates and then send tau to 0 and hope to be still able to, that the topology in which the limit holds is strong enough in order to allow to deal with these nonlinearities. And actually, the only thing that I would like to point out here is that we don't need compatibility of the initial data. Why is this so? Well, it's maybe also intuitive to see here, we don't need to do any time integration. We do need, of course, a third initial condition because it's a third order in time equation. But well, this third order term just goes away in the limit. Well, it does not just go away, but eventually it goes away after some being treated appropriately. Another very interesting and actually challenging limit is the limit as the diffusivity of sound. The delta here goes to 0, because the delta is the one that appears with the strong damping. And the strong damping is what, as I pointed out previously, is heavily made use of to prove global in time existence, because this strong damping term allows to achieve relatively high order energy estimates and so on and so forth in order to deal with these nonlinearities. So what happens if delta is set to 0 or if delta tends to 0? Well, there have been some results around on the case of delta equal to 0 with for the Westerveld equation, so without the gradient nonlinearity. But it's also interesting to include it because it's the more general model, and to even maybe go to this higher order model with the limit in delta, and also to look at convergence rates. And that's actually what we did in these joint papers with Vanja Nikolic. And of course, to mention previous work, in case of delta equal to 0, what is also clear is one cannot expect global in time existence of solutions anymore. That's already the consequence of the quasi-linear wave equations paper of Alinak of 1999, because it's then clearly quasi-linear wave equation. Well, let's skip this gradient term. So it actually this equation with basically this term was more or less considered in this paper, and it was shown that in two space dimension it blows up in finite time. But local in time existence can still be shown also for this third order J and GT equations, also including the gradient nonlinearity, and for the equations with delta, so with damping, one can show that really the solutions converge to the respective inviscid solutions, so those with delta equals 0. One can even show convergence rates as delta tends to 0. Recently, we have also been looking at fractional order equations, namely, especially in nonlinear ultrasound applications. It has been known already for many years, actually, that damping in human tissue does not take place usually with this, so to say, simple strong damping term, but one has fractional damping due to the fact that the damping is frequency dependent. So if one looks at the behavior and frequency domain, then one has frequency dependent damping. And this is not just linear with frequency as it would be for this damping term, but it goes with a certain power law that one can extract from measurements. And so people have been looking at these fractional order equations in acoustics also for several years by now. What is always important in the context of using fractional models is really the modeling part. Because, well, to some extent, this fractional order business is becoming a bit inflatoric, one should say, or one should maybe not say, I don't know. So sometimes people are suspected, at least, of just adding fractional terms instead of integer terms just for the fun of it, which, well, to some extent might be justified in mathematics, but it's less so in applied mathematics, where one should really take modeling serious. And we tried to do so and actually also derive models from physical balancing constitutive laws. And actually, I should say not me, but Vanja Nikolic again did so. And we had really nice references for this purpose. So we had actually ended up with 4 different fractional models. This is just one of them. And you see, for instance, the exponent, this fractional exponent alpha here appears at several points. That's really what emerges from the modeling here. And what you also see here is that formally, if you let alpha tend to 1, we end up again with one of these classical higher order models, namely the JMGT equation. And our aim was here to really do again this limiting process in a rigorous way, which, as you can imagine, is challenging due to the fact that the leading order derivative also depends on this limiting quantity. Okay, now let me move on to one more analysis modeling topic, namely coupling, which is also important in the context of these focusing principles. So this is a repetition of a slide that you have already seen previously. And let's focus mainly on this side here, because here the focusing is done through a lens, which is made of different material. So also the equations, the material is different inside and outside the lens. So that's the setting that we are going to look at. And so what we have is some fluid which behaves non-linearly acoustic, and a lens which is linearly acoustic or actually even elastic. And so the whole domain, which is the union of the light blue and the light brown one, is composed of 2 sets with different equations on them, or at least different material parameters on them. In particular, one cannot expect high regularity solution to exist throughout the domain. That's the problem here with our approach of avoiding degeneracy, because of these jumps over the interfaces and also the fact that the domains are not particularly regular. You might see these cusps over here, so and re-entrant corners. So it's non-nice domains. So this H2 of omega regularity that would be needed for getting this embedding into L infinity of omega and avoiding degeneracy is not present here. So what our workaround for this was to include some, well, one might call it regularization, but actually to some extent it's also justified physically. So there exists what is called power law fluids, where the damping is done by a P-Laplace operator. So it looks like this. So this is our previous damping term. So P times Laplace of ut. And then the introducing the P-Laplace damping gives us this additional term here. Well, it's clear if you have P larger than 1, then this gives us higher regularity after appropriate multiplication. For instance, you might easily guess that we would multiply with ut here. And so then one can get energy estimates that gives boundedness in the W1 P+1 norm. So if P is sufficiently large, this embeds into L infinity of omega again. What is another aspect here is to write these equations in a monodomain formulation, because in principle, the physical quantities that live in these 2 different domains are at least related to each other. So if we model the lens also by an acoustic domain, then it's basically the same physical quantities. It's always the acoustic pressure inside and outside the lens. It just comes with different material parameters. And actually inside the lens, one would expect that the sound propagation is still linear and also basically without any damping. So both the nonlinearity parameter and the damping parameter can be set to 0 in there. And outside it will be non-zero. And then it's clear one can write the whole thing as an equation on one domain. It would not be correct to take this equation on one domain, because then we would have jumping coefficients that would be hit by divergence, and then what would get into trouble about high regularity solutions. But in this setting, it's still separate equations on the two subdomains coupled by interface conditions. The natural and also physical interface conditions are continuity of pressure and continuity of velocity. So inside and outside the lens, of course, it's clear the particle velocity needs to be the same because, so to say, the particles stick together over the boundary. And likewise for the pressure, we have the same pressure from both sides. Mathematically, the way we demand for the continuity of pressure is really in a trace sense, and the way in which we demand for continuity of the velocity is in a variational sense here. And it's also due to this nonlinear damping, so this P-Laplace damping term that we have introduced, it's actually not the velocity itself, but a sort of modified velocity that is continuous over the boundary. And with this, one can really write it in a monodomain formulation with this weak formulation. So we have put the divergence over to the other side, and the boundary terms vanish due to these interface conditions. One can also do this in case of an elastic lens. And well, the quantity is now not the pressure anymore, but it's the velocity. So we have a particle velocity on both sides in both domains. And so this is a physical quantity that makes sense in both domains. Inside the lens domain, inside the solid domain, in this Helmholtz decomposition that we make use of here, there's both components present. Outside in the fluid domain, recalling that the velocity is irrotational there, we only have this gradient part of the velocity. And so we can, so to say, switch between these two cases, also between the linear elasticity inside the lens and the nonlinear acoustics outside by this K tilde here, which is, sorry, it should be a K tilde down here as well, which is 0 in the elastic domain and non-zero only in the fluid domain. So this is the part that gives us the nonlinearity. And yes, and it also only affects this gradient part of the velocity. The coupling, the interface coupling is via the velocity again, but this time in a trace sense. And now it's a balance of forces, namely a balance of normal stresses, more precisely here. And this is again demanded in a variational sense. And it's also something like a modified stress, because again, here we have this nonlinear part, which of course from one side just vanishes from the elastic side. So this term back here just goes away there, but it's still there from the fluid side. Okay, now let me come to numerics. Before doing so, I have a question: how much time is left?
I'm sorry, I'm checking. Let's say 5 to 8 minutes.
Okay, thank you very much. Mm-hmm. Okay, then I can say at least a little bit about these non-reflecting boundary conditions and why they are important in the context of acoustic wave propagation. So the main point is that waves usually propagate in free space, and but usually one would like to restrict computations to a limited domain that is not too large, because the larger the domain, the more computation effort it costs to do simulations. And so in the setting that we have seen before, where we have this bowl-shaped piezoelectric array here, so this is again just a cross cut, so this is just half of the cross cut here. The wave is excited down here, and then it will travel through the domain. But in our computations, we have cut the domain here. So this is just a symmetry axis, so there's no problem about this. But these boundary parts are the essential ones. So if one just puts homogeneous Neumann or Dirichlet conditions, then the wave will not be happy about then, because it will be reflected by them. So we have put sound hard, that means homogeneous Neumann here. And you will see that here on the left side, waves will get reflected, whereas we would like to see these waves just travel on through these artificial boundaries and travel on through free space. And that's actually going to happen here on the right-hand side, where we use absorbing boundary condition. So let me just start this small finger movie. It's just snapshots. And you see the wave is excited down here. So right and left is the same for the moment. And also, while the wave propagates through here, there's not much of a difference between the left and the right. But when it starts hitting the boundary, and especially this sound hard on one hand and absorbing boundary, things start to differ. So you will see in a moment here on the left-hand side, the wave will get reflected. It's still already being reflected, as you might see here. And on the right-hand side, it's traveling through. That's what it's supposed to do. So how to get such boundary conditions mathematically? So this is best explained by means of the one-dimensional scalar wave equation. In the 1D case, also, as you certainly know from the derivation of D'Alembert's solution, one can decompose the wave operator into two parts, either way. And that's actually the PDE. But actually, both of these parts corresponds to two different traveling directions for the wave, going right or going left. And of course, at the boundary at -1 and +1, in order to avoid reflections, one is supposed to annihilate these reflected parts of the wave. So those that would travel inside the domain. On the -1 boundary point, I don't attempt to show this here in my video, because it will probably be the wrong direction for you. So on this -1 boundary point, it is this part of the wave operator that we are supposed to annihilate in order to avoid reflections. And on the x=1 part, it's this part of the overall wave operator. So that's clear. And this can be generally written as, let's put it here, as the normal derivative, which is either plus or minus dxu being equal to a multiple of the time derivative on the boundary. This also works in higher space dimensions, but these, as they are called zero-order non-reflecting boundary conditions, only avoid reflections of waves that hit the boundary really in perpendicular directions. Waves that come in at oblique directions are partially reflected, and that's why one also needs higher order non-reflecting boundary conditions. And just to give you a flavor on, well, they are still decreasing energy. This is just a simple computational exercise. If you multiply, as you are used to when deriving energy estimates for the wave equation, if you just simply multiply with ut and integrate with respect to space and time, you see that this term here is a dissipative term. It rise to a dissipative term on the boundary. Just to give you a flavor on how they look like in higher space dimensions and in the nonlinear case, well, let me point out the role of the effective wave speed here. So what you see here, that's the maybe most simple case, Westerveld equation of nonlinear wave propagation. And if you divide by this nonlinear term here, 1 + ku, then you get something like an effective wave speed, namely c divided by 1 + ku. If you plug in this effective wave speed instead of this c up here, you really end up with these zero-order nonlinear absorbing boundary conditions. And that's not just by just doing it, but this can be justified by analytic methods. So if you go to higher order, then they become quite complicated. Also that, as expected, because they are supposed not to only annihilate orthogonally hitting waves, but also tangential components. It also involves tangential derivatives. So let me just skip over the derivation here and show you at the very end, more or less, some numerical results that are supposed to show that it really pays off to use these nonlinear and also higher order non-reflecting boundary conditions. Again, returning to the setup of a high intensity focused wave excited by a piezoelectric array down here, and it's supposed to eventually focus up here. So this gamma A is the absorbing boundary, or one could also call it artificial boundary. The A could stand for absorbing or artificial here. And here's also a Neumann part, which is responsible for modeling the excitation. And so if one just looks at the results, so this is a reference solution that has been computed on a very large domain. So no reflections here. So really the waves just going out. Time is proceeding here from left to right. And from top to bottom, at the top, we have the, so to say, ideal, perfect simulation on a more or less unbounded domain. And here is what you get with bounded domains over time, so at different time instances. From left to right, first of all, just with first order linear absorbing boundary conditions, then with zero order nonlinear boundary conditions, and this is with first order nonlinear boundary conditions with these complicated formula that I've shown you on the previous slide. And I also here have to confess that it was really not me who did the implementation, which is actually quite challenging, but it was, I hope I mentioned him somewhere here, it was Igor Shevchenko who did these nice simulations. So let me skip over the optimization part. Sorry, it's time. I'm running out of time as always. It's my fault as always. And let me come just to a quick outlook just on other recent work. So I've already mentioned about fractional order damping. This is another, actually a bit more simple fractional order model that has been around in the acoustic literature already for some time. It goes back to Caputo, but also Margaret Wismar has been using it. So we call it Caputo-Wismar model. And we have been using it both in the sense of analysis, but also in the sense of inverse problems, because there are really nice inverse problems also arising in nonlinear acoustics. And one example for this is, so to say, the last item that I would like to talk about, nonlinearity imaging. So this nonlinearity parameter, let's call it K of X here, is actually a function of space, because nonlinearity depends on the tissue in which the wave propagates. So it's really different for different types of tissues, and therewith it gives a way of imaging. So especially medical imaging. And so since it's about nonlinear wave propagation, one really cannot just do it by using the usual ultrasound imaging methods, but one really needs to do it via the PDE, where this K appears as a coefficient. And we also have recently done some work on this, some kind of preliminary initial work. So there's lots of interesting topics in modeling and analysis of, in the context of high intensity ultrasound, for instance, coupling to temperature, when one thinks of thermal therapy, and also cavitation is a phenomenon that really plays an important role there, and that needs more modeling and in particular more mathematical analysis. So sorry, I still went over time. Let me apologize for this, and thank you very much for your attention.